binds to iron. Okay? So once that oxygen binds, it's a little easier for the next one to bind. Okay? And a little easier for the next one, and even easier for the last one. Meaning it has a higher affinity for it. So it's more difficult to come off when we get to the tissues. Whereas when we get to the tissues, once a couple of come off, it's even easier for these to come off, which is good because if we're that low of PO2, the body really needs the oxygen. So as it's going through the blood, oxygen is moving in and binding, as it's moving through the lungs, oxygen is moving in and binding to the iron. At the same time, because we're still going by alveoli, we're continuing to add oxygen to the plasma. By the time we leave the lungs, in the ideal situation, our hemoglobin is 100% saturated. That's how we measure the amount of oxygen on the hemoglobin, is what percent of saturation do we have. And our PO2 of the blood is 104. All right, we could get higher. How could we get a higher PO2? It's so close to 100 that some students confuse that with 100%. We're not talking about 100%. We're talking about numbers of oxygen.
If you were like in an oxygen chamber?
Yeah. They haven't caught on very strongly in the United States, maybe in Las Vegas, but Japan has oxygen bars. You go in there and you breathe in high concentrations of oxygen. You're going to drive this up to 120 or 130, right, breathing in pure oxygen. That goes up to 130. This is going to go up. Okay? So the higher the percent of oxygen that you breathe, the higher this PO2 is going to be, because the higher this PO2 is. So this isn't stuck at 104. That's just typically what we are at sea level. Now, if we get up to 4,000 feet, remember PO2 in the air is dropped. When we get up to 10,000 feet, PO2 is dropped even more. And so it becomes critical. If we have too low a PO2 here, we're not going to have enough oxygen to stay bound to the iron. All right. So that leads us to the information that's on the next page, the oxygen dissociation curve, page 60. This is a series of graphs that illustrate the relationship between PO2 and hemoglobin saturation that we can look at different conditions. So if the blood has a higher pH, if the PO2 is low, if it's fetal hemoglobin instead of maternal hemoglobin. So we're looking at the attraction between oxygen and hemoglobin as it's affected by the PO2. So this again is identified as an oxygen dissociation curve. Some students get a little anxious when they see a graph. All right, so I'll take it slow. Which line is the x-axis? Horizontal or vertical?
Horizontal.
Horizontal. Okay? And this would be the y. This tops off at 100%. We can't get more than 100% hemoglobin saturation, right? So the y-axis is the value of hemoglobin saturation. So 50% of the hemoglobin is saturated, or 75% of the hemoglobin is saturated. So we have 50, that's a different color so you can visualize it. Okay, guess my phone. And then the x-axis is the PO2. Do you notice I drew that a lot longer than the height of my y-axis, because we can go over 100 millimeters of mercury. That's not saturation. So put 100 millimeters of mercury, 50, 25, 75. So that's our PO2 in the blood, all right? So it's arterial PO2. Now, what we're looking at is as we increase the number of oxygen molecules dissolved in the blood, we're going to increase the saturation of our hemoglobin. What we're looking at here. It's not a straight line, okay? A direct relationship would be as we increase PO2, we increase saturation in a direct one-to-one relationship. That doesn't happen, all right? If we had a very, now with this, let's say if we were able to saturate our hemoglobin at a very low PO2. So if I could saturate my hemoglobin at, say, a PO2 of 30, I'm way up at about, 18,000 feet. My graph looked like this. That would seem to be really nice. What's the problem with that? I'm saturating my hemoglobin. I'm carrying 100%, every single one of my iron ions has oxygen bound to it at a really low PO2. I mean, like I said, I could live, 3/4 of the way up the Himalayan mountains to Everest, and I'd have plenty of oxygen, which is great. But I wouldn't be able to live there. What's the problem with this picture? Huh?
It won't go down to 0?
You're on the right track.
Can't unbind.
Exactly. One man said you can't release the oxygen. If it's saturated at a PO2 of less than 25 here, PO2 in my venous blood was 40, my tissues would be dying for oxygen, and the oxygen would just be circling around the body, stuck to the iron, never coming off. So we don't want that chemical attraction between the electrons of the iron and the oxygen to be so high that the oxygen and iron are glued together and nothing ever comes off. That's the problem with carbon monoxide poisoning, part of the problem, okay? So, all right, let's reverse that. Because we want to saturate our hemoglobin where the purpose is to deliver it to the blood. Sorry, the purpose is to deliver it to the cells, to the tissues. So let's give it a really low. We'll put it way down here. Now, it comes off really easily, but we can't carry very much. We might as well not have any hemoglobin at all and just carry what's in the blood. So what actually happens is a very unique situation that provides us the best of both situations. Over here, where we have a PO2 of 100, that happens in the lungs, right? Where we have a low PO2, where the cells are using up oxygen, happens in the tissues. And so we see this kind of sigmoidal curve where we have a plateau, but we also have a steep gradient. The plateau is where we have the lungs providing oxygen. And what it indicates, and I don't have this quite accurately drawn, but down to about a PO2 of 80, between 75 and 80, we can get 100% saturation of our hemoglobin. So we can go up to Tahoe, all right, and not suffer adverse effects while we're skiing. We might be a little fatigued, but we're still getting 90 to 100% saturation of our hemoglobin. The plateau, the steep gradient, the steep portion of our curve is at the tissues. So once the PO2 gets below 60, why would the PO2 get below 60?
It's been used.
let's say now that we're in our tissues, here's our capillary. So instead of being our pulmonary capillary, this is our systemic capillary. And we have tissue cells whose mitochondria are using oxygen to make ATP. The free oxygen, remember PO2 is free oxygen, it's oxygen that's dissolved in the plasma. The free oxygen in the blood is going to be moving out and being used by the cells. And what's going to happen to our PO2 as that occurs? Remember, our PO2 is 104. As the oxygen moves out, PO2 is going to decrease. Because PO2 is not measuring the oxygen that's bound to the hemoglobin. It's measuring the amount of free oxygen dissolved in the plasma, giving off that gas effect. So as oxygen moves out and into the cells, that's not oxygen, it's the nucleus, our PO2 now is going to start to drop. And when it gets to a PO2 of about, I said 60, it's closer to about 45 or 50, then the oxygen that's on the hemoglobin starts to come off very rapidly. So right at the range where the tissues need a lot of oxygen gets freed from the hemoglobin. Okay. Now, in trying to illustrate this concept to students, one of the best illustrations I had was playing musical chairs, right? So we don't actually play it, but, so let's say I have 15 chairs lined up. This will be in the lungs, all right? And 15 people, and the music plays, and everybody runs around. Or maybe I have 30 people, the music plays, everybody runs around, stops, 15 people take their seats. All right, that would be the oxygen-bounded hemoglobin, and the 15 people running around would be the free oxygen dissolved in the plasma. But I have a place. For everybody that wants to sit, I have a place. All right? So as we're moving through the blood, and some of the hemoglobin that's free diffuses out, our seats start to change. They were like almost bucket seats. To get out, you had to kind of push yourself up, and because you were sitting like this, you had to kind of push yourself up to get your bottom out of the bucket seat. But now the seats change, and the seats are almost vertical. So that represents the attraction, the chemical attraction between oxygen and hemoglobin. So while you're running around, when the music stops and you sit on that seat, almost as soon as you sit, you start to slide off. Okay? So now, if we look at it in that aspect, the saturation of hemoglobin becomes a little bit easier to understand. So, if I'm sitting here and I'm about to slide off, and I do, and there's no other oxygen around, that seat's going to remain empty. Okay? The hemoglobin's not going to be saturated. But if I have 5 people and we're running around this one seat, if I slide off, there's going to be another person to take my place. So while I'm not sitting on that seat, somebody else is, and that seat is occupied. The hemoglobin is still saturated. So that's how PO2 affects saturation. If there's enough oxygen around, even though there's a low affinity for iron to oxygen, as soon as the oxygen comes off, another one will take its place. If there isn't very much oxygen around, then there's longer and longer periods when the hemoglobin doesn't have iron bound to it. So we're going to look at that in relationship then of the shifting of this curve either to the left or to the right. So if I shift the curve to the right, typically what shifts is the steep portion, which shifts the most. So I'm still able to saturate my hemoglobin at about the same range. But what about the affinity between hemoglobin and oxygen? So if I look at 50%, the amount of oxygen dissolved in the plasma required to saturate my hemoglobin 50% is to take more or less when the curve shifts to the right. It takes more. So if we go back to that chair, it means that the angle of that chair has increased. The oxygen isn't staying on there very long. And so to keep oxygen on there at all times, I need to add more oxygen to the plasma. So again, if I was playing musical chairs, not only is the chair at an angle, but it's been greased. So when I sit on there, I slide right off again onto the floor. If I don't have a whole bunch of other people, that chair is not going to have very much oxygen on it. So I have to add more people to the game to make sure, because people keep slipping off. So I have to add more people to the game to make sure that any one time I've got somebody sitting on that chair. So when I shift the curve to the right and it takes more oxygen dissolved in the plasma to keep that hemoglobin saturated, what does that say about the chemical attraction between the iron and the oxygen? Has it gone up or has it gone down? It's gone down. All right? So it doesn't stay bound very long. So anything that's going to cause oxygen and hemoglobin to separate and come out, have oxygen separate from the hemoglobin and go to the tissues more easily is going to shift the curve to the right. Right? So this is shifting the curve to the right. So I've listed some factors in your lecture notes. A decrease in pH, meaning the pH is becoming more acid. That changes the shape of the hemoglobin molecule, changes the interaction between oxygen and iron that makes it more difficult for the oxygen to stay associated with the iron. And so it comes off more easily. Increase in temperature. Increasing the temperature increases the kinetic energy. All right, so it's bouncing around, trying to keep a kid in their seat. It bounces off of its interaction with iron. Both of these events occur under conditions of exercise. So it makes sense. Also another one, an increase in carbon dioxide, which then directly will lower pH because carbon dioxide will become carbonic acid. But carbon dioxide also binds to hemoglobin, as we'll see tomorrow. And when it binds to hemoglobin, it binds to the protein part, not the iron part, but it changes the shape of the hemoglobin enough that it makes it more difficult for the oxygen to stay there. So it's like greasing that seat that we're trying to sit on. All right? So all three of these are going to occur with exercise. There's some additional factors listed on page 62. One of them is a molecule called Q3-BPG or GBG. This is made by erythrocytes under conditions of low oxygen and decreases the ability of the hemoglobin to bind to oxygen. So it's kind of an internal, get rid of the oxygen ticket. Yes?
Can you say one more time just that really basic sentence? You said it's shifting to the right because...
Okay. So when it shifts to the right, maybe I should just add that up here. There is a decrease in oxygen hemoglobin affinity. It becomes more difficult for the iron, or maybe I should just put iron. It becomes more difficult for the oxygen and the iron atom to form a chemical interaction to share electrons. And so when we do have chemical reactions, they usually are only temporary anyway, a chemical bond. And so a strong bond just means those two molecules stay interacting with each other for a longer period of time. A weaker bond, there's less time, all right? So with this, we're saying that at any given time, the oxygen, this oxygen that's here, when it moves to the right, that oxygen is going to separate from that iron more quickly. With a high PO2, there's going to be another oxygen right there to take its place. So we don't know, we can't tell that that oxygen has come off. Because every time we check, there's an oxygen there. We don't know that it's a different one or that it's the fifth different one. So as the attraction between iron and oxygen decreases, and it comes off quicker, more quickly, if we don't have another oxygen there to take its place, it's going to be less saturated. So the more quickly it comes off, the more oxygen we have to have around to make sure there's always something there to bind to it and keep it saturated. So back to the musical chairs, the more difficult it is for me to stay on that seat. As soon as I sit on that seat, I slide right off. If there isn't another person right there to take my seat, that seat is going to be unoccupied, and the hemoglobin partially will not be completely saturated. So the more quickly I slide off that seat, if I stay there for 5 minutes, I could only have maybe, one other person roaming around, and I come off and they're right there. But if I come off and I'm sitting on the ground because I just slid off, and then someone else sits there and then they fall off and slide on the ground, and I haven't gotten up yet to be able to take a seat, and I don't have anybody else available, that seat's going to be unoccupied. So the less time, the less attraction there is between iron and oxygen, the more surrounding oxygen in the plasma I need to have available to take its place and make sure it stays saturated. So these are all conditions that decrease the amount of time the iron and the oxygen actually stay bound. Okay? So we have to just, and that's good in situations, so these are all situations in which oxygen is being used up, all right? So it makes sense that the oxygen requirement would be higher. All right, so then the opposite is true if we shift our curve to the left. If we shift our curve to the left, and I redraw this curve, now it takes less oxygen dissolved in the plasma to make sure that the hemoglobin is saturated. So back to our musical chairs illustration. When I sit on that seat, I'm glued to it, okay? It's like that bucket seat, or maybe it's a folding chair that's partially collapsed. And it takes me a while to wiggle out of it. So I'm stuck there for a longer period of time. Because of that, I don't need as much free oxygen in the surrounding. If I'm going to stay here for, 30 seconds instead of 2, then I need less oxygen out here to replace me, because most of the time I'm there, I'm not coming off. So when the curve shifts to the left, it shows an increase in the chemical attraction between oxygen and iron. So I need less PO2, I need less free oxygen in the plasma to maintain my saturation. So this is an increase in oxygen-iron affinity. Obviously the opposite of all of these, right? So an increase in pH, a decrease in temperature, a decrease in partial pressure of carbon dioxide, a decrease in 2,3 BPG. In addition to that, fetal hemoglobin. Remember when we talked about after baby's born, we see an increase in bilirubin because fetal hemoglobin is being broken down by the liver, all right? Fetal hemoglobin is different because of one of the chains. There's alpha and beta proteins, and there's a different component in the fetal hemoglobin, and it holds on to the oxygen longer. It can be saturated. That helps it get saturated in the placenta, because remember the blood coming to the placenta is coming from the umbilical arteries and has lower oxygen content. So the mother's blood is coming from her arterial blood, but it's not coming directly from the lungs. And so the whole gradient has shifted, but because fetal hemoglobin has a higher affinity, we don't need as much PO2 in the mother's blood to get to the baby's blood, so the baby's blood can have a lower PO2 and still get saturated in the placenta. Also, the fetal hemoglobin isn't affected by the 2,3-BPG, so it can get saturated at a lower level. All right. The fetal hemoglobin isn't affected by 2,3-BPG. Carbon monoxide. Carbon monoxide, carbon dioxide will bind to hemoglobin, but it binds to the protein part. Carbon monoxide competes with oxygen for iron. And once it's there, it stays there longer. So it has a higher affinity. And once it's there, the oxygen that is there doesn't come off as easily. Okay? So this is a form of carbon monoxide poisoning, is a form of hypoxia. Interestingly, you can have a normal PO2, but if you have carbon monoxide bound to the iron, the oxygen that is down there can't come off, then we have that higher affinity, it shifts to the left, which is bad. It's great for binding in the lungs, but it's bad when we get to the tissues, because it means that when we're at a lower PO2 in the tissues, guess what? The oxygen's not coming off. So this is how people can suffocate with carbon monoxide poisoning and still have bright pink cherry red lips and fingernails because they have a normal PO2. They have oxygen bound to their hemoglobin, but it's not coming off. Okay, so the tissues, remember, can't live with just the PO2 that's in the bloodstream, that's in the plasma. All right, we're going to stop there. We will look at carbon dioxide transport tomorrow in our other classroom. So today we've got a couple of things going on. Remember, our quiz is covering histology. And then I'm going to, while you're studying for that, I'll give you about, I'll check back with you at 9:30. So take a break and review for that. I'll check back with you at 9:30. I'd like to try to get lab started at 10 or before. Okay, so a little bit of range there to see how you're doing. Remember, this lab quiz is similar to Tuesdays as far as model content, but with an emphasis on histology. So at least 3, probably 4 histology slides recognizing respiratory, the pseudostratified columnar epithelium, the olfactory epithelium, which is the olfactory neurons, the various airways. Microscope slides are over here. These are your quizzes from Tuesday. And then after we end that first part of lab and take the quiz, we'll start the measurement of pulmonary volume. Okay? This is going to be a problem taking the quiz if I can't get the slides projected to work. So let me work on that too.
Yeah.